All right. So let's talk about the solar system. Study of the solar system, as I've explained, led to the birth of science. Eventually, it led to Newton, who showed that mathematics worked, and he reduced the solar system problem to one parameter, the inverse square law, versus some other power. He didn't know why, but that's all right. Okay, so what do we have in the solar system? What have we got? We have the sun and 8 planets, comets, asteroids, dust, and debris. What happened to the 9th planet? Pluto. Sorry? It got demoted. All right? Pluto didn't disappear, but we saw lots of other Plutos in space. And if there's 9 planets, you're going to be 100 planets. I don't think people we're used to the idea of thinking we have 100 planets out there, so we demoted all of them. They're all what are they called? Planets? What the hell's the name? Huh?
I think it's planets.
Dwarf planets, yeah. Is that right? Dwarf planets, okay. All right, now, what do we say about the planets? There's something very strange. The Earth, the Sun, has all the planets revolving around. Now, you can use a right-hand rule to tell what this angular momentum you characterize with the right-hand rule. I'm doing it with left hand because I have to. Now, you wrap your hand around the direction that the solar system is going. All right, everybody wrap your hand. And your thumb points up. All right? That tells you, see, if you do it the other way, it'll point down. So the angular momentum is the direction of your thumb. So the angular momentum of all the planets, we'll say, points up. The angular momentum of the planets in their orbit points up, but the angular momentum of the planet's spin also points up. Everything in the solar system, with small exceptions, has the angular momentum matched. Why? How did that happen? Okay? That's a fundamental question. All right. This has to tell us something about how the solar system was formed. All right, so should I turn another light off?
Yeah.
Okay. Okay. All right, the solar system. Now that is a picture up there, a drawing of the solar system, approximately in the right scale, except the planets are drawn too big. Mostly there's empty space. The planets are in about the right position, scaling, and you see that on small scales is all the rocky planets. The sun's there, Mercury, Venus, the Earth, Mars. 4 rocky planets. Then on the outside is a comet belt, or asteroid belt it's called, a lot of broken up pieces of rock. And then Jupiter, then Saturn, Uranus, Neptune, and Pluto. Now Pluto's drawn here, but you note that Pluto is not in the same plane as the other planets, The dwarf planets in general are out of the plane. They're way up here, down here. That's one thing that distinguishes them. Okay. Now, average properties of the planets. How do we measure the average property? Well, we use Kepler's laws. And we characterize them by what is the average density. You all know density. The density of water is 1 gram per cubic centimeter. It's defined that way. That was how they defined gram. Okay, a gram per cubic centimeter is the density of water. So in a solar system, the mass of a planet is equal to the volume of times the density. This has the units of mass. And the volume is 4 pi over 3 r cubed, the density. Now, if you play this game, the sun's average density is just about that of water. It's a gram per cubic centimeter. So, okay, Jupiter has a similar density. And other planets, Saturn is lower than 1 gram per cubic centimeter. It's, say, 0.8 grams per cubic centimeter. That would mean if I could find an ocean that was big enough to settle Saturn in it, Saturn would float. Okay? So just like ice is a little less than 1 gram per cubic centimeter and it floats, so would Saturn. Of course, finding an ocean is a problem. The outer planets, though, they all have low density, and they're known because their density is low, they're known as gas giants. 0.7 to 1.3 grams per cubic centimeter. But the inner planets, Mercury, Venus, the Earth, have high density. And the Earth is 5.3 grams per cubic centimeter. Now, what do we compare that with? For example, granite, solid rock of granite, is 2.7 grams per cubic centimeter. The Earth is much heavier than granite. Basalt is 3 grams per cubic centimeter. Now, why is that? Where is the mass of the Earth? Here, the rock, you think the Earth is made of granite and basalt. That doesn't add up to give you the right density. So we'll see what happens later. Okay, the Moon and Mars have density intermediate to this and the outer planets. That tells us something. All right, and so now, if you want to ask questions about the solar system, what is the question? For example, why are all the rocky planets close to the Sun? And the gas giants are far away from the Sun. Is this universal? Do we see the same pattern when we look at what's known as exoplanets around other stars? And the answer is no. We don't see that as universal. And that is a very puzzling result, and people are working on what it means. This is an observation that was surprising. What determines whether a planet has an atmosphere? For example, Mars has no atmosphere, effectively. The Moon has nothing. The Earth has our atmosphere. Venus has a very thick atmosphere. Why? Why is Venus so different? Mercury has nothing. Okay, why does Venus have a hellish greenhouse? Really hellish greenhouse, making the temperature of Venus, as I said before, up to 700 or 800 degrees Fahrenheit. Or centigrade, I think. All right, very, very hot. Hot enough to melt metals. Why? Why is that? It's a little closer to the Sun. It should be hotter because of that, but shouldn't be that hot. Why is it like that? Okay, and now the other question, where's all the water on Mars? Mars used to have water. You can tell by the canals or the dugout craters, the stream beds have all the signs of water, but doesn't have it now. What happened to it? Okay. Why do some planets have a strong magnetic field while others have only weak fields? The Earth has what's known as a half a Gauss field. Jupiter has a very strong field. Saturn, all the outer planets have it. Mercury has nothing. Mars has nothing, effectively. Venus has, I don't remember what Venus has. Why is that what we see? What can we say about that? What is the nature of the predominant wind patterns seen on the Earth and the other planets? Why do they take the form they do? Why is our dominant wind in California from the west? Whereas if you go south to the equatorial zone, the wind blows east to west. And then it reverses. Ours is west, east to west, south of us. Why? What in the world makes the wind do that? Why? Why? So these are questions that we want to know. This is something technical, and I'll explain why that's important later. Okay. How about the internal structure? How do we know what the internal structure of the Earth is? How do you possibly guess? How do scientists know that the internal structure has a massive core of very heavy elements like iron? All the iron of the Earth is sunk. Why? Why did that happen? Okay, so the formation of the solar system. You have to explain this. The planets are isolated. The orbit of every planet is almost circular. Not quite circular. Some of them, they're elliptical, but they're close to circular. The orbit's all in the same sense, in the same plane. Spin of the sun is aligned. Spin of the sun is aligned with the planetary orbits. As I said, spin of the planets usually aligned. Orbit is, they're all in the same sense. And why are they rocky planets toward the sun, gaseous and icy planets away from the sun? Why does that happen? And we see asteroids that come into Earth, are orbiting in space, and the asteroids that have crashed in the atmosphere and left rocks below are old, very old. How do we know that? All right? And furthermore, the comets are like asteroids, except they have ice. Asteroids generally are rocky, but the comets are rocky plus ice. The comets are mostly resident very far from our solar system. And why does that happen? Okay, so a lot of questions are posed about the solar system. You haven't thought of these, but they're real questions that scientists know, and they want to understand why. That's the nature of science. Why? I mean, they have to explain this. Can they explain this? Okay, so let us take the first business. This is a short video that shows about what is the collapse of the solar system. Okay. All right, so, okay, so we've got a gas cloud. It's kind of hard to see now. Here's a gas cloud. What happens to this gas cloud? There's a gas cloud in interstellar space. It's just there. The gas cloud it has gravity. So what's it going to do? It'll attract itself. But the cloud also, just randomly, the cloud is moving this way and that way. And if you add up all the motions, it has an angular momentum. The angular momentum is known as a conserved quantity. Angular momentum you're born with is angular momentum you keep forever. All right, now how does this work? The cloud collapses, but the angular momentum causes the cloud to keep spinning. The spin of the cloud has to be conserved. And that tells you that it must be conserved. Now I'll show you an example.
I think you have to press repeat if you want to see this.
Press what?
Press repeat.
Press what?
Repeat.
Oh, yeah? I don't think so, but... Okay. All right, let's do it again. All right, now we're going to do it again. And she's spinning a little bit as the cloud is collapsing. She's spinning slowly, and then she pulls her arms in. As the cloud collapses, that is effectively like pulling your arms in, and the skater spins faster, and so the solar system spins faster. It hasn't any choice. It spins faster because of conservation of angular momentum. All right? And that is why. That is why so many things in the that we examine astronomically are actually disk. They collapse into a two-dimensional system, and then they can't collapse further. let me show you. Here's this movie again. Now, there's two views. There's a view of, here's a view of what we saw before, and here's a view from the side. Now, when this happens, as this happens, this shrinks, and this, you can see, is shrinking but spinning. All this spinning, 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 and here it is. It shrinks to a disk. And what that represents is a state of minimum energy. It loses all its energy, which it can do by radiating away. And the cloud at the same time cannot radiate away the angular momentum that it carries. The keeping of the angular momentum is like a skater. She's spinning, and the result is that you keep the same angular momentum you're born with, and virtually any cloud has a little bit of spin. All right, now what are these clouds? We'll talk about that in a little bit. Okay, now, when the cloud, after the cloud has collapsed, it is warmed by the sun. We have a proto-sun in the center. This isn't a real sun like ours. It's a sun still in the process of collapsing, but it radiates anyhow. It radiates, and we know that it's warm near the center. It's cold further away. So we can draw an imaginary frost line, where beyond this point, the cloud is frozen. And that means that it's lower than 0 degrees Celsius, 273 degrees Kelvin. And that's where water freezes. All right, so all this material in the solar system is primordially hydrogen and helium. And that doesn't collapse anywhere. We know hydrogen and helium, they're very light, and we know that hydrogen and helium do not collapse. There's nothing it'll do. It just goes away. Except in a really heavy planet. The planet has to be extremely heavy to hold on to the hydrogen and helium in the solar system. The planet can be heavier where on the other side of the frost line, outside the frost line, the gas is moving slowly, the water freezes, and it can make bigger planets, we think. All right. Another picture of our, this is out of our book. Here is the solar system in the process of being born. Now, the solar system is mostly gas. This is a real picture, right, of our solar system. Okay, and what's happening is that some rocky stuff forms, this rocky stuff all over the place. The sun is radiating, it's hot. Some gas has, this is a planet that has absorbed all the gas around its disk. These rocky protoplanets are all over the place. They result from the collapse of the primordial gas that's in the solar system. So if you then, all right, so this is what I'm saying. Close to the forming sun, the hydrogen and helium will not accrete onto the planets. They're too warm. All right, but further from the sun, water is, there are icy moons and planets, they could easily form. A lot of the moons on the planets that you looked at are made of ice. It's pretty neat. You know, our moon is made of rock, but the moons further out are actually composed of ice. Pretty neat. Now, the gas giants gave what is known as planetesimal, gave planetary gravity boost to these planets. I'll say what gravity boost is in a minute or two. All right, so the idea is you start off with a cloud, it collapses to a disk. The disk fragments into lots of little fragments, and small gravitational attraction breaks it up into very small fragments. On the outside, these are made mostly of ice. On the inside, it's something else. It's rock. And they are attracting all this material. All right, so if you look in other planets, we can look at the formation of other planets. When astronomers have pointed at planets. Now, if they point at a planet, they've got to watch out because the star they're looking at is so bright. They've got to put a block, or called an occulting disk, that in the focal plane to just get rid of the sunlight, because it's so bright you can't see anything. The contrast of that to the planet is too large. So they put an occulting disk on it. Here's the occulting disk, and here is a star. This is blocked out, and here is a disk around the star. Here's some more. These are the occulting disk, and here's a disk seen edge on. Now look at the size of Neptune's orbit. This disk is very large indeed. Compared to Neptune's orbit, which defines more or less as our solar system, this is huge. Here's the solar system, the scale on this one. All right, this is the same device, this is one camera. Here's another camera on the Hubble Space Telescope. And the scale shows you that the disk formed is really quite large. All right, I don't know if that's always that way, but this one in particular is quite large. Now here's another picture. This is an occulting circle this time, and here is a disk. All right, and here is 100 astronomical units. The distance to Neptune is about 40 astronomical units. So this system is larger than our solar system. Okay, here's another one. They're in here. This is an occulting system. The rays are an artifact of the instrument. But here, there is a ring is seen in this guy. All right? It turns out there are planets in here too, and you can see them move. You take pictures at different times and you can see them move. That's really incredible. You're looking at planets in a nearby star. It is amazing what astronomers are able to do. This used the technique of adaptive optics to get this thing. I believe this was taken with the Keck telescope. All right. Now, all right, so again, Jovian planets are on the outside, terrestrial planets are on the inside. They're molten. When they're born, they're really a mess. When the Earth was born, it was a molten rock. It was just like slag you take out of a furnace to make iron ore. Really, really, really hot. All right, the Jovian planets had a core of rocks and ices and all kinds of little, we think, all kinds of little ice clouds about them. All right, now what happens is you've got hundreds of little rocky planetesimals orbiting the star. Here's an example. Now this is a computer simulation showing what happens. Now, you let the thing orbit, and eventually the planets are attracting each other. Gravitationally, they attract each other, and that will cause them to get close together, and then they merge. And bang, they have a hell of a collision when they merge. All right, and so it's 30 million years to go from here to here, where you've got it down to a few. And then you wait for 441 million years, and four planets is all that remains. That's a long time, 440 million years. You know, think about 440 million years. Well, in astronomy, that's okay. That's a normal time. And so the planets form after that time in this computer simulation. So this is probably what happened in our solar system. Okay, now the Earth and the Moon, here's the Earth, here's the Moon. The Earth at the end of this planetary formation is still picking up nearby rocks, and they make a hell of a splash when they hit it. They crash, and the energy of them coming in is so much it can melt the Earth's core, melt the Earth all the way around. The Earth, and you can see the Earth just covered with craters from previous collisions. Now, a question emerges as to why the Moon, why we even have a moon that's so big. The Earth has a very large moon. It's the only planet in our solar system that has a large moon like that. Why does it have it? All right. Well, it probably is an accident of the Earth's formation. The Moon has a very low density. It's about the density of granite. The density of the Earth is twice as much. That is volume per cubic centimeter. How'd that happen? What they think happened is that a planetesimal, came in, bang, it hit the Earth at an angle, it didn't get absorbed, and it led to a cloud of junk, mostly melted granite, around the outside, a whole ring of granite that are gradually accreted into the Moon. I mean, it's pretty, if you were here 4.5 billion years ago, it would be quite dramatic. Okay, now here's a question. Here I want you to talk to your neighbor again. Why are all the planets born hot? So think about this. Is it conservation of thermal energy, conservation of energy, or just conservation of angular momentum? So talk to your neighbor, or none of the above, all the above. Talk to your neighbor until you come up with an answer. Okay, I want to hear some talking.
I think it might be C.
We got to talk to somebody.
He's got this idea.
Yeah, he knows.
Yeah.
All right. Do you know that most answers are just going to come through C? So,
Yeah.
Most answers are C?
I don't know. That's what I've always been told, since 5th grade.
Yeah.
So,
Just bubbling all C.
Oh, okay. That's conservation of thermal energy is your answer. Okay, fine. What do you think?
So that's why I'm kind of thinking.
All right, everybody have an answer? Okay. First of all, is it conservation of angular momentum? Hold your hand up like this so you don't have to stick it up and embarrass yourself or whatnot. Just hold your hand up. Okay? Nobody's answering. Okay, fine. Conservation of energy. Conservation of thermal energy. Hey, come on, some of you, all the above. Most of you didn't vote. Or I couldn't see your hand. All right, fine. You think it's all the above. Well, all right. It is not conservation of angular momentum. Okay, that has to do with, it doesn't really have to do with energy. It is not conservation of thermal energy. I don't even know what that is. All right, so thermal energy is internal heat, but that's not even conserved. You know, like for example, when I drop a ball or I hit a ball in tennis, it gets hot. And I've told you energy is conserved. Well, where did the thermal energy come from? It came from hitting it. But that wasn't, if you take the beginning of the exercise, you have no thermal energy, and later you have thermal energy. It's not a conserved quantity. The conserved quantity is the energy. The energy is conserved. And that's a very fundamental point. We will use that again and again and again in this course. Energy is a conserved quantity. You make energy somehow, and what you have is conserved. All right. All right, so now you have, here we're talking now, let's change subject a bit. We have comets, a lot of comets around here. They're out and they're moving around apparently randomly. And they're not really in the solar system. They're out of the solar system. Here, for example, is the plane of orbit of Jupiter, orbit of Neptune. And they have cleaned out the comets in the inner solar system. They're swept out. But the comets, there's something called a comet. The Kuiper belt is a ring of comets in this region outside of Neptune. And then there's something called the Oort cloud. And these things are very, very far away. They're up to 20,000 times the distance from the Earth to Sun. They're really out there. All right, and why are they there? Okay, and we know that the stuff in there is really old. How do we know it's old? If I got a rock and you try to date it, how can I tell how old it is? So we'll talk about that also. Yeah. Okay. All right, so the origin of the asteroids and comets, how did they get formed? Okay. Here, for example, is Jupiter. Jupiter orbiting around. And it happens to have something called Trojan asteroids that are exactly, here is the Sun, here is Jupiter. You can draw a triangle here, and it's 60 degrees from here to here. 60 degrees is the angle between those. And another case is 60 degrees. Why are they there 60 degrees away? A rock, an asteroid. Why are these asteroids inside of the orbit of Jupiter? Okay, so the solar system was cleared of gas in its early phases, but it was not cleared of planetesimals. Why? Well, what clears them? It is the big planets like Jupiter and Saturn, which pull on them, and and so the Sun was actually making the orbit, but then Jupiter comes along and disturbs the orbit. And that disturbance of the orbit is what actually makes the planetesimals move out of the solar system. Now, these rocks in here presumably would have formed another planet. But they are prevented from forming a planet by Jupiter. Jupiter is very heavy, and it pulls them at random times and prevents them from attracting each other to form a planet. It won't happen. All right. Jupiter's gravity prevented them from forming there. And the fact that there are these Trojan asteroids, it turns out that if you have an orbiting planet, it will have, out here, it has a what's called a Trojan point, where the three planets can orbit around. The whole system is stable to orbiting around and around, with this thing staying 60 degrees behind or ahead of Jupiter. That's just something that comes out of the mathematics of orbital mechanics. You don't have to know that, obviously, but that is a true statement. So those Trojan asteroids they're there, and they're fine. Okay, the other ones would have formed, except that Jupiter is tugging them all the time, and typically, Jupiter comes around and pulls it, and they can't. That overcomes the gravity it had between each other, so that it never really had time to form a planet. Okay, now, how do the planets all get born in the same plane? Here's a question, another question to discuss. So discuss it with your neighbor. The initial energies were aligned. The plane was aligned with the galactic plane. We have a galaxy that has a plane, and the solar system is aligned with it. Or finally, a bit of primordial junk has some initial angular momentum. All right, so talk to your neighbor, and let's see what we say for that.
Well, I think I might abandon my C hypothesis this time.
You've got a chance out of 3 of being right.
There we go. Do you really? Yeah, one will get. Yeah, one of us will get. I got B.
All right, let's take a vote. How many say it's A, initial energies were aligned? That's good. Okay, it's not A, because energy is a scalar, so-called scalar. That means it just has a number. It doesn't have alignment. It is a momentum that has alignment. I have a momentum moving that way, and that's very different from momentum moving this way. Momentum is a vector, so-called. Have you studied vectors in high school? Okay, you know all about that. All right, excellent. All right, so energy is a scalar. It doesn't have a direction. How about the plane? Did it align with the galactic plane? Okay, a few. Anybody? No. All right, how many say it is C, a bit of junk? Nobody. The rest of you guys aren't. You got to answer this thing. All right. Okay. Would it be better? Would it be better if you had cards and held up a card? Yeah. One. Yeah. All right, Eric. We got to get these cards. Okay. I'll get cards for you. What color should I use? Red, blue, green? Huh? No red? Why, that's a wedding color? Huh?
Stanford.
Oh, jeez. All right, red, blue, green, and I don't know what the other color is. Huh?
Pink.
White? Pink? All right, fine. It has to be a basic color that I can see because I'm partially colorblind. And so, okay. All right. The answer is, of course, it is C. The junk, we had some junk that just happened to be orbiting around, spinning around, and that junk, that angular momentum, was preserved. There was nothing to get rid of it. If the angular momentum is preserved, that means it is preserved. The angular momentum it is born with is the angular momentum it has today. All right? Okay. All right, now, what did the cloud, or what was the primordial cloud that led to our solar system? Here is something known as the gaseous pillars. This is a region of the sky, intergalactic plane, that is a beautiful region. This is a picture from the Hubble Space Telescope, a lovely picture. And this thing is not a cloud like around here. It is a big cloud, and I mean big. Okay? Let's see if I can make this. Does this? Here. These clouds, right here, for example, and right here, and right here, and right here. These are protosystems. They're stellar systems that will collapse. The whole cloud is huge compared to a solar system, weighs hundreds of times what a solar system does, and it's more or less it's in the process of formation. A lot of the cloud is being eradicated, is being evaporated. Yes.
How do you calculate the weight of the solar system?
How do you see the a representative density, and you just add it up. Density is a big cloud. You know what the density is. Multiply that times the volume, and that's the mass. Real easy. More or less. That does it. You can do it that way here. All right. So you see this bright star behind it? The bright star is a blue star, is putting out light in the ultraviolet. The ultraviolet light is hitting cloud, and it causes the dust in the cloud to evaporate. The cloud is like a morning fog here in Berkeley, in the Bay Area. The fog is made overnight as the Earth cools down, or something like that, and then the sun comes up, heats the cloud, and it goes out. It just evaporates. What happened to the atoms of the cloud? Where'd they go? It was made largely of water vapor. Where'd they go? Did they disappear? So where are they? Nothing. All right, what has happened is the cloud consists of lots of little molecules, little droplets, fine little droplets. You know, you can see this when you go in an airplane and you pass through a cloud bank as you're climbing. You can see that the cloud bank, if you look closely, the cloud bank's made up of tiny little droplets of water. And with the sunlight, the droplets evaporate, and then you can't see them. It's transparent at that point, the water, just you don't see it, but it's still water. The cloud presented, it was a scattering center. The light came down, the cloud bounced it around, and you can't see through the cloud because it bounced the photons around, and that happens around a small particle in the atmosphere. If you break the cloud up into individual atoms, then they can't scatter the light at the same rate. They scatter a little, but not at the same rate. So that's why clouds are white, and other things are, the atmosphere is transparent. Okay, so stars are evaporating the clouds, except it's very hard to evaporate something that is bound by gravity. You're not going to get rid of material that is self-attracting and is holding together by gravity, no matter what you do to it. It's going to stay there. Gravitation holds it in. So, meanwhile, the cloud, a very complicated process. This cloud in the past probably was big enough to cover the whole region, and it may have formed, that blue star may have formed out of the cloud. The blue star formed out of the cloud, and then it turns on, and it shines so brightly that it evaporates everything around it. Everything. And so you see this. It's amazingly complicated, very beautiful. Okay, here's another example. Here's a solar system, and look at this bow shock. This is a shock of the gas that's moving. Which way is the gas moving? Right or left?
Right.
Moving this way? Or moving the other way? It's to the left. Because this is just like a bow shock in a boat. You see a wave that defines the direction of the motion. If a plane comes by supersonic speed, this shock becomes very sharp, and it propagates outward, and it's such a sharp shock that when it hits you, you see bang. All of a sudden, you hit a wave came through, and it was a sonic shock. This shock is supersonic as well, and it's generated by this cloud over here, or this star over here, and it is pushing the gas around. Now, these are mechanisms for condensing the gas, and it might be that these processes are responsible for the formation of planets, or formation of the whole solar system. Now, we think that the Earth, the whole solar system, was very close to a supernova 4.5 billion years ago that blew up and sent a tremendous shock wave through space, and that shock wave collapsed some gas around it and probably made the whole solar system. And we are a result of a nearby supernova, which is pretty neat. You think about it. All right, and there's evidence for it. There's other evidence. Okay, here is nebula. Here's more results of nebula. Here, for example, I showed you this at the beginning of the course. Here is a dark spot. This is a spot that is illuminated. It's something known as a nebula, and it puts out light. So with that light, you see that the thing in front of it, this guy, is absorbing the light. All right, and it has a star in it as well. Here's another one. All right, so these are all solar systems in formation. Now, these are solar systems right now that are forming stars. Okay, not 4.5 billion years ago. Right now. Okay, so that is just one example. The solar system. We see sun, stars that are very young, way under, say, 50 million years, and suns that are extremely old. Ours is middle-aged, 5 billion years, but we see lots of stars of 10 billion years. Okay? It's amazing. You know, they formed a while ago. All right, so you see these disks. All right, these are some of the objects. Here's another one, a blow-up of this solar system in formation. Very beautiful. That's what they are. Now, another question we have is a puzzle that we worry about. The sun is spinning. The sun is spinning around the same direction as everything else in the solar system. But the sun is spinning too slowly. If you can calculate the amount of spinning that the sun should have as it collapses. And it has a lot of mass, and it's like the skater who pulls herself in tight, and she pulls herself down to a line. And the line has to be spinning incredibly fast to make it. But the sun doesn't spin that fast. It's relatively slow. And what we think, we're sure that the sun is slower because it had a magnetic field, The magnetic field has lines that come out of it, and it's just like an electric power generator. The magnetic field spinning around encounters the magnetic field of the Earth, of the spinning disk, and the sun is spinning faster, and the fields don't stay aligned. The sun spins too fast for the disk spinning. And just like an electric generator, when they're not the same, there's a torque on the sun. It would need something to keep the sun spinning. There isn't anything. The sun, instead of continuous spinning, slows down. In a power plant, the sun would get it spinning from water falling down and generating torque, generating energy, which can make the sun spin faster. Well, that is not possible in the solar system. But otherwise, it's the same process, and the sun is slowing down. All right? And we see stars, and they're all slower than they should be, and that means that they had magnetic fields, and they torque themselves down that way. There's no other way to do it. Okay. Now, if you look at a solar system, it's spinning and spinning and spinning, and material accretes around it, but that's not a solar system. That's Jupiter. Jupiter is just a piece of this big solar system. It was spinning and spinning and spinning, and it broke off and is spinning and spinning and spinning in the same way. And that's why the spin of everything is the same. It hasn't any choice. All right? Does everybody understand that? Questions? Okay, the angular momentum is lined up. All right, it's now the beautiful thing is to look at the moons of Jupiter. Is Jupiter up, Eric? Is Jupiter up? Yeah.
Let me check.
Well, did you see it when?
Oh, I wasn't at the start party this week. That was
Who saw? Did anybody see Jupiter? Huh? No. All right. Jupiter is unfortunately down. I mean, it means it's up in the daytime when you can't. It's too bright to observe it. All right. So it's too bad. It is? Okay. All right. We can't point that far down. If you try to point at the horizon, you'll see a building. So, okay. That's a shame because it's nice to see the moons of Jupiter. Okay. The moons, the spinning material had moons that had collapsed out of it, and these moons formed a miniature solar system. Jupiter is a miniature solar system. Jupiter and its moons are just like the sun and its moons. It's a miniature solar system. Okay, now we see some amazing things. This is a picture of various colors. Some of that's ultraviolet light, some of it's optical, some of it's X-ray. And this is a star is forming. The star is spinning around in this axis. So the angular momentum points downward. Okay. Here is the sun. And it's got a disk of material that could make a star. Maybe there's another material. The magnetic field is what is constrained by the outer part of the magnetic field is shown here. And this has all the ingredients of a smaller star in formation. Same physics. Okay. Now, we want to figure out how old the solar system is. All right, how do you tell how old something is? Well, we use something you all learned, I hope, in school. Everybody learned about dating material, like use carbon 14 to date artifacts. You date, what do you date? Clothes and people and all that stuff. Now that carbon 14 only works to ages of order 10,000 years or younger, because carbon 14 decays too quickly. There's nothing left after that time. So astronomers and geophysicists actually have to use a slowly decaying piece of the Earth. The decay of potassium-40 to argon-40 is one such object, and the decay of uranium to lead. All right, now how does this work? All right, so we know what the half-lives are. And that's the time for half the material to disappear, to radioactively decay. Now, have you seen the concept of half-life? Yes? No? Hold your hands up if you have. All right, you've all seen that. Okay, fine. So half-life, all right, and decay is a random process, and that enables us to do it, to do the method. The potassium half-life is 1.3 years, and you know, after 2 half-lives, goes to half and a half again, and that makes a quarter of the material remains. Okay, so all right, and we can write that as a fraction of the remaining material is 1/2 times the time over tau, the half-life. All right, and that tells us how much of the material is left. For example, if you potassium-40 decays to argon-40. So here's potassium-40, here's the abundance. The fraction is 1 at the beginning, and then 1 half-life, it's a half. 2 half-lives, it's a quarter. 3 half-lives, it's an eighth, etc. All right, and so you can compare the ratio of argon-40 to potassium-40, and from that ratio, learn something about the age of that rock. You try. All right? Okay. Now, the rocks, you do this dating method, and you find that it's really hard to find rocks older than 3 billion years. Pretty rare. Okay, but if you look at meteorites that come in from space, they have ages that are dated to 4.6 billion years using the same method, this dating of potassium-40 versus argon-40. Now, you can think about this. If the material is molten, then the argon-40 will bubble out of it. All right, so that's not a reasonable thing to say. You can say that 4.6 billion years is the age when the rock solidified. Okay, it doesn't say how old the whole system is, but it says that the rock solidified 4.6 billion years ago. That's what you learn from that. And you see, if you go out and date the rocks on the moon, you get a similar figure. 4.6 billion years. All right, and it's that dating, and this is the most accurate dating possible. That dating has to be the same of the entire solar system. It's not as though the solar system was 3 billion years, and then you say, "Oh, I'll have some comets and take them from someplace else." Well, it doesn't work that way. The comets and the planets all formed at the same time. It's hard to date the planets, but the dating of the comets and meteorites is more secure, and you get these ages. 4.6 billion years. Okay? As I said before, there are systems in the galaxy that are twice as old. And there are systems in the solar system, in the galaxy, that are very young, 50 million years or less. Now, one thing you might wonder, how can he know the age of a star? How the hell is it possible to date the age of a star? Because we can't go out there and can't ask the star anything. How is that possible? All right, now I don't expect you to know this, but you will learn in a few weeks or month or so or less, you'll learn how to date the age of a star. It's an amazing technique. Astronomers have devised this technique. All right? And it's pretty damn, it really works. All right. So, just to review what we said, you see a rock, and the argon-40, the potassium-40 is 1. How old is the rock? So talk to your neighbor, and let's see who remembers what I said. Don't look at your notes. Don't look at your notes. All right, so how old is it? You guys could talk until you get the right answer. Hmm?
Billion years.
All right, everybody have an answer? Okay. Let's go backward. Is there enough information to determine? No, not enough information.
Okay.
Now, note, I don't say how old is the molten rock. I said how old is the rock. Rocks are solid. And that means argon is trapped in it. It can't get out. Okay? And so is potassium trapped in it. So this is a ratio we measure. A geochemist measures this, and he says it's 1. All right. Is it this old? Huh? No? 2.5 billion? 1.25 billion? Come on, vote, 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 vote. All right, 1.25 billion. All right. 1.25 billion was the number I told you. That was the half-life of the potassium. The potassium has lasted 1 half-life because the remnant of it formed argon-40. The argon-40 all came from the potassium in the rock. So half of it's decayed. Yeah. Potassium. Oh, you know that's wrong. What is potassium? What's this?
K, it's just K.
K. I'm sorry. It should be K. I'm sorry. Now what's kryptonite? Kryptonite. Wait a minute. What's that? What's the? Is that the name? Krypton? Okay. What's Krypton's symbol? You chemists? KR? Is it KR? All right, sorry, I meant potassium. Okay, I better fix that. Okay. Okay. Now, Cassini is a mission that is orbiting Saturn right now. And it has sent some amazing probes into one of the moons and it's given a lot of beautiful pictures. But there's a problem with Cassini. Cassini is very, very heavy. It's heavier than other rockets we've sent. It had a lot of stuff on it. So as a consequence, they made a mistake. I mean, maybe the rocket just went the wrong way. Here is the Earth when it launched. It launched it inward. I mean, Saturn, we didn't tell, got to tell them, Saturn's out here. It's outward. But no, they launched it to Venus. Now, wait a minute. And so it flew by Venus in 1998. Took a long time to get there. Then 1999, it flew by the Earth. No, wait a minute. Where's 3? Okay, flew by Venus, and then when it was opposite Venus, it fired its rockets, so it would go in further, or fired it one way or another, I don't know. And then it flew by Venus again in June 1999. Then it flew by the Earth in April of 99, and it flew by the Earth pretty close. It was within, I think, I don't know. It was pretty close to the Earth. Now, and then it got flung out of the Earth. Whoa! Flung out, and it went by Jupiter in the year 2000. And then it rammed, and Jupiter flung it further, and it went to Saturn. Now, how's this work? Yeah. Yes, it uses not to spin, but to boost the orbit. And we'll talk about what it means to boost an orbit. Okay, may as well say right now. Let's see what it is. All right. Suppose here's Jupiter, and a rocket ship comes by, and it goes in a parabolic orbit or something, and you know that the closest approach to Jupiter is like this, and you also know that a parabolic orbit is symmetric. This is the same as this. All right? In other words, the speed here is the speed is the same here and here. We'll call it v. That's the speed, and the opposite side of the planet, speed is that. We know that's what happens. Kepler's laws tell us that energy is conserved, and it does that. Now, let us then, okay, we're in the frame of view of Jupiter, which actually is moving this way in the orbit around the sun. So we have to go into that frame, you have to add motion to make the planet seem like it's in the frame of Jupiter. All right? And that means that looking at it from here, looking at it outside, here's the sun, here's Jupiter, here's Jupiter. The planet comes in with some speed. It doesn't emerge at the same speed. It emerges with a speed that is corrected for the orbit of Jupiter. And that means that you can, if you you make the thing come in right, the planet comes in with speed v0, call it, right here, and it exits with a speed v0 plus the speed of Jupiter, because it has to do that in order for it to be symmetric in the frame of view of Jupiter. This is called gravity boosting. And this is how Jupiter cleaned out the solar system of junk. You have junk orbiting close in. Jupiter boosts it to a high velocity, and it doesn't come back to the solar system. It's good to get rid of all the comets, because otherwise they'd be bombarding the Earth. Even today, you have a lot of crashes on the Earth. Instead, we had a crash. When was the last big crash on the Earth? Anybody know? Dinosaurs. You know, you used to have a green tail and feathers. You know, I wish I had feathers. But, you know, they got destroyed when the Earth got hit by a comet 65 million years ago. Now, a few comets are in the solar system, and occasionally we get hit. But if Jupiter hadn't cleaned out the solar system a long time ago, we'd get hit every year. Well, not every year, but every 1,000 years. Every million years would be bad enough. I don't know how often we get hit, but it'd be frequent. All right, so the gravity boost was essential to get Cassini out to the orbit of Saturn. You just had to do it. Okay, so, well, I sort of gave away this. All right, why did NASA do this? Why did it work this way? No, wait a minute. All right, to give good pictures of Venus, NASA made a mistake. They sent it the wrong direction, but they made it up for it by fortunately having the planets in just the right orbit, right position, so they could boost it to Saturn. Or we couldn't send a heavy payload out there, and so we did this. All right, or none of the above. I just gave the answer away. Okay, it's C.
I think it's C.
Don't think about it. Okay, we had to do that. Okay, so all right, that was essential to do that. Now, all right, this gravity boost I just told you. In the center of mass frame is one way to think of it. Center of mass frame is this, like this. In the planet's frame, ingoing, outgoing velocity is the same, but here in the other frame, you end up with a different behavior. Okay. All right. You add back the velocity of the planet, as we did, and that gives you the speed, more or less. Okay, so the rocket is boosted. The satellite speed is boosted by this close encounter. Now, here's a question for you. Where is the energy coming from? After all, the rocket got energy from these boosts. It must have come from somewhere. Where do you think? Where did the energy come from? Wait, I'll call on you later. Anybody else? Anybody know? You know, it didn't happen. The energy wasn't created. It happened. It got it from somewhere. Where could it have gotten it from? Huh? Or did we send in a beam? We sent the energy out to the rocket at the right time. We sent it in a beam. Yeah. No? No, that's wrong. Okay. Because if that were the case, there'd be no reason to go by the planets. I mean, why to go that way anyhow? You know, why don't we send a rocket ship straight to Saturn? It took 7 years to do this, to get that orbit. That's a long time. And it'd take you only a year or two if you just went directly. You know, I think I forgot to turn. Oh, it's on. All right. Anybody else? Here.
I mean, I know that Cassini had a plutonium-based reactor inside it. So basically, I mean, when the
All right. You're saying the radiation.
no, not necessarily. I mean, like when you're traveling in space, there's no friction when you're traveling by. Like if you're moving towards one direction, you will keep moving towards that direction.
Yeah.
So basically, I played a computer game before that is based on this concept of gravity boost, and it basically.
Gee. Oh gosh. I'm sorry. I gotta quit. I'm sorry. I'm sorry. No. It is the energy. This thing. The energy of this thing is is coming from the planetary orbit. The orbit of the planet moves around, and a little of it was stolen by the satellite. Just a little bit of the energy was stolen. Okay, I guess everybody's got to go. I'm sorry I ran so late.